Well, I'm often accused of talking over, but given the current circumstances, I decided to talk under, since I have, according to my calculation, 10 minutes to deliver the talk I prepared, and we all, of course, want to hear Xian Yang. So I will skip rapidly through my talk. I will be back in Singapore and would be delighted to give this talk at another occasion. But instead, in the talk, I describe the great achievements of elementary particle physics, the standard model based on non-abelian gauge theories and its great success, the electromagnetic, strong, weak interactions, which are all non-abelian gauge theories, the difference between electromagnetism, which has only one charge and doesn't confine electrons, which we use in we can extract from the atom, the quantum properties of vacuum, which are inherently quantum mechanical phenomena, here illustrated with a quantum oscillator, and there should be some way of going on. And then I discuss the non-abelian Yang-Mills gauge theory of the strong interactions, chromodynamics, where the quantum fluctuations in the vacuum modify the force between quarks so as to make them asymptotically free or non-interacting at short distances and yet confining at large distances. I discuss a bit quantum theory of non-abelian quantum chromodynamics that leads to confinement and the success of quantum chromodynamics. I then go on to discuss the open questions remaining after the fantastic achievements of the standard model. There are still many open experimental and theoretical questions. I discuss one of the great motivating themes of the last 30 years, the search for unifying the various forces of nature, as described so successfully by the standard model, how they fit together neatly, how they can appear so different at low energies and yet unify perhaps at very high energies, the various speculations that have arisen from this search for unification, which might be a coincidence, we don't know yet, how I discuss how the forces might unify and the speculations about supersymmetry, which we search for and continue to look for at the LHC, how it solves various problems, which might or might not be a valid clue. We have yet to see. The astronomers' discovery of a new kind of matter, which we haven't yet detected on Earth, or we don't know exactly what it is. It might be the candidate predicted by supersymmetric theories. We have yet to see. That might be a clue, might be a coincidence. This is what we're looking for, our colleagues at the LHC. We hope to see it within the next few weeks or years. And that would be, in a sense, a discovery of the quantum dimensions of space-time. Let me pause in this rapid discussion to say a word about the future of elementary particle physics. There are two possibilities, as always. You can be an optimist, you can be a pessimist. The extreme pessimist scenario is that we've more or less learned everything we're going to learn at the energies that are readily available now and in the near future. The recently discovered Higgs shows no deviations from the standard model, and supersymmetry or other beautiful speculations don't show up. we don't detect dark matter on Earth or in the sky, and we don't know where the next interesting threshold is. Perhaps we have to wait till the Planck mass. What to do? In that case, of course, we must fully explore even higher energy, shorter distances to gain clues or to discover what we speculate about. On the other hand, the extreme optimistic scenario says that we will see shortly, as the LHC turns on in a few weeks, or actually this weekend, we will see deviations from the standard model. We will produce supersymmetric particles. We will detect dark matter and produce it in the LHC or underground, and we'll have very strong guidance to the next step. And that, again, this next step will involve exploring in detail the new physics that will be discovered next week or next year at the LHC. In both cases, we must fully explore the 10 to 100 TeV energy range, and there has started already, of course, to be very serious discussion of how to go beyond the LHC. The International Linear Collider project, or a linear electron-positron collider, is being advanced in Japan, and we hope that they succeed in doing that with the help of partners around the world. CERN has detailed plans, very hard to see here, I think, but for a large accelerator, which would reach 100 TeV by going under Lake Geneva and the Jura Mountains. In principle, you could fit such an accelerator at Fermilab, but there's little discussion of that. On the other hand, there is very serious and exciting discussion to build a electron-positron collider, which would then morph into a proton-proton collider in China, what I like to call the Great Collider. And I regard that as a ambitious yet totally achievable and fantastic opportunity for Chinese and Asian physics. Then I go on to discuss how the forces might truly unify at the Planck scale. I discuss string theory, which is our best hope for unifying all the forces of nature, and probe the issue of whether string theory could indeed successfully unify the subatomic forces in gravity and provide an explanation for the standard model and the unanswered questions that it leaves. I discuss a bit the way I view the current framework of theoretical physics, which contains both quantum field theory, where the standard model is embedded, and string theory. I discuss a bit how I would have discussed a bit how this enlarged framework gives us new insights both into gauge theory, string theory of QCD, quark-gluon plasma, quantum phase transitions in condensed matter physics, the quantum version of what Michael was just talking about, and might help resolve some of the puzzles of quantum gravity. And most importantly, I end with a discussion of the various speculations we're currently deeply involved in what is the true nature of space-time, with the input of our deeper understanding of Yang-Mills theory and of gravity and of string theory, and which has led us to believe that space-time is an emergent concept, and we are struggling to formulate the rules of physics without imposing space-time from the beginning. I also discussed the issue of how we are being forced in trying to unify all the forces of nature together with gravity to construct a theory of dynamical space-time, namely of cosmology, and that gives us, requires us to confront the Big Bang, or the initial conditions of the universe, and to ask a question which physics so far has been able to avoid: what are the initial conditions? How did the universe begin? Since already Einstein taught us that the answer to a question of what is dynamical space-time involves the history of the universe as a whole and requires us to address what happens at the beginning and perhaps at the end. And here we simply don't yet know what the rules of the game are. And I end with saying that the most wonderful theory of we have a wonderful theory of elementary particles, but the most interesting questions remain. We have fantastic instruments like the LHC, and in the future, perhaps the Great Collider, and fantastic speculations, but the best is yet to come. Okay, so I did my whole talk in 5 minutes. And if I had time, which I now do, I was going to add a coda, which I will do without rushing through. And the coda, is to address a more philosophical question, which you might wonder when I started asking some of those absolutely impossible questions. How did the universe begin, and what is the nature of space-time? And that is, in this area of what I call fundamental physics, but it really is the exploration of the basic laws of physics and the basic constituents of matter, now involving quantum gravity in addition to the subatomic and subnuclear forces and particles. Can this enterprise keep going ad infinitum? Now, and there are really three issues here. One is that it might end in the sense of we might construct the final theory, and then we would obviously get to the end of the rope, no more questions to answer. So can we construct a final theory of physics? The second possibility is that, well, we're just too dumb. We might simply be too dumb to go on and answer those questions or continue to understand at an even deeper level the laws of nature. And third, we might lose the will to proceed. And I want to discuss briefly these three issues and give you my view. So could we construct a final theory of physics? Is there a final theory of physics? In my opinion, like everything, every good question, we should geometrize it. So I regard this as a question, in my opinion, about what I call the geometry of knowledge. Now, there is a very popular conventional geometrical model of knowledge called the onion model. The onion model is a model that says knowledge is like an onion. You peel away the layers, and eventually you get to the core of knowledge. I don't like this model. It brings tears to my eyes. And besides, it's inside out. Well, the way I view things is that we live in a sea of ignorance intellectually. And now we are pushing out into that unknown and mostly unknowable sea of ignorance, the region of knowledge. So we're going outwards instead of inwards. Now, the ignorance that we're aware of, however, is only on the surface of the region of knowledge. So we can only formulate questions close to the borders of what we already know. And this geometrical model explains a fact that we're all aware of, namely, the more we know, the more we realize we don't know, and yet we get a bit wiser. So that is simply a geometrical consequence of this model. So knowledge is the sphere of knowledge expanding into a sea of ignorance, and knowledge obviously increases like the volume of this region, whereas ignorance increases only as the surface of this region, because we're only aware of the ignorance at the border of what we know already. That explains, as we learn more, knowledge, of course, goes up like the volume, but ignorance also goes up, and this is something we all experience through our life. The more we know, the more we realize we don't know, and new questions keep arising. And yet, of course, wisdom, which is sort of like the ratio of knowledge to ignorance, increases as well, since volume increases more rapidly than the surface, at least locally. So now the question of can we construct a final theory of physics is really the question, is there a finite amount of ignorance or not? A final theory would answer all the questions, at least at this so-called fundamental level. And that might be possible. That happened in the exploration of the Earth. This map, Eurocentric map of the world in the Middle Ages, had the sphere of knowledge, which is this area around the Mediterranean, and even Sweden is someplace on the map. And everything beyond was the sea of ignorance, where you couldn't draw the map because no European had explored it. And people for many centuries Europeans explored the Earth. At first thinking it was flat. Some people thought so, and one would go on exploring forever, but the Earth wasn't flat. It's topologically a sphere, and sooner or later we ran out of ignorance, and all the maps were completed, and the explorer societies were closed down. So in the case of physics, the question is the sea of ignorance compact? If it's non-compact, unbounded, infinite, like the flat Earth, then we can go on in fundamental physics forever. But it could be that is just the way it looks at the moment, as the Earth looked flat for a while. And actually, there's a radius of curvature, and sooner or later we'll discover the radius see the horizon in the sea of ignorance, and start the amount of ignorance will start decreasing instead of increasing, and we'll realize that we're running out of ignorance and we're approaching a complete theory of everything. I'm totally agnostic to this question. It could be one way or the other. I see no way of deciding. At the moment, of course, the sea of ignorance looks pretty flat to me. Ignorance, new questions keep arising, no matter how much one learns, and there's no sign of a horizon. Of course, if it is compact and there is a final theory of knowledge as there was of the Earth, this wouldn't be the end of physics, because, as Michael illustrated, there are fascinating questions at every level of complexity, which might all follow in a reductionist sense from some final theory, but still most of the interesting phenomena and discoveries to be made in science arise in the levels which only in a absurdly reductionist scheme could be derived from that understanding. But there's another obstacle, as I said, to being able to go on in either scenario, and that is that we might simply be too dumb to proceed. I mean, it's pretty arrogant. Isn't it arrogant for us, the human Homo sapiens at this stage in evolution, to assume that we are able to comprehend the most fundamental and conceptually challenging questions in fundamental physics, since we know very well that our fellow species on Earth are simply unable to do so. I have not been able to teach my dog quantum mechanics, and I am sure that's not just because my teaching is so bad. The dog, or any of our cousins on Earth, cannot understand what the laws of nature as we have already understood them, not to speak of the future. Why should we assume that we are able to do so? Surely we might be like dogs. There might be concepts that are required to formulate the laws of physics beyond some stage that we can't construct using the state of the human mind at this stage of evolution. Well, there's a reason here, I think, to be optimistic. One is that what is special about Homo sapiens, special about our species, is that we possess language. And language, like mathematics, its highest form, has infinite capacity. We're well aware that mathematics has infinite capacity, but even normal language that an infant learns so easily by imitating, listening to his parents, a child, as Chomsky pointed out, once they learn at a very early age human language, are able to utter sentences that have never been uttered before. And that infinite capacity to formulate new sentences is a kind of infinite capacity of language which we alone possess. And that infinity might not be big enough of an infinity to comprehend everything we need to about the real world, but it might be. So again, I'm agnostic, but there's hope. There's also absolutely no sign that we are getting to the point where we're faced with questions that cannot be answered. The questions we face now appear to be more difficult than those we faced in the past, but that might just be because those of us who contemplate that phenomena are getting older. If I look at young people who now have to cope with non-abelian gauge theories and string theories and M theory and who knows what, they are able to learn to master all of the knowledge that we've accumulated over the last millennium and arrive at the boundaries of the frontiers of knowledge and make significant contributions to advancing into the sea of ignorance, just as they did 20 years ago or 50 years ago or 100 years ago. There's no sign. I would think that if we were getting to the point where the questions were becoming like dogs, unable to comprehend the Schrödinger equation, then graduate students would take longer and longer to get to the frontiers of knowledge and to make big new advances. There's no sign that that's happening. And finally, even if we had some inherent limit to our intellectual capabilities, we would simply modify ourselves. We would tinker with our genome or use machines connected to our brain, as we're probably going to do anyway, and that might help us go on and on. I think the real issue about going on forever is that we might lose the will and the means to go on. Big science and elementary particle physics, which is absolutely necessary to answer some of the questions that we now face, and big science and astronomy and cosmology, which is absolutely necessary to answer some of the outstanding questions of the history of the universe, are both getting bigger and bigger, more expensive. Timescales are getting larger to do the experiments that are needed. And society, or even us as a community of educated scientists, might lose the will and the means to go on. And here I can only say that I hope not. And end this coda with the quote that is on David Hilbert here's grave: "We must know we will know. Thank you.